Okay, here we are, microphone still active, so let us go back to our proof. So, we want to compute the circulation of the field on this square and find the Gauss-Green theorem formula. And remember that the square or the rectangle in which we are computing the circulation has to be understood as one of the internal rectangles of this grid, but not the whole grid, the part of the grid which is bounded by the curve C on which we integrate. Okay? So, here we are, and then we start with the computation. Nothing but a long and boring computation. So, if we call Ci the rectangle, the circulation of F on Ci is equal due to the fact that R dot in this first side is 1, 0, dot the field. And T here is going from 0 to delta x, and this is why we have these extremes of integration. Okay? And this is the first term in the sum, first side of the rectangle. Second term, the second term here will be the second side, and we have t that goes from 0 and delta y. And now the speed, the velocity of the point that follows our parameterization of this side is 0, 1. And this is why we have here the second term like this, like 0, 1. Then we go to the third term. And in the third term, we have this parameterization this time. I explained in the last video. The x-coordinate is x plus delta x minus t. So when t gets delta x, we are here. And the velocity is minus 1, 0. So this is why in the third term, that refers to the third side of the rectangle, the velocity is minus 1, 0. And then we move to the fourth and last side, where the velocity we are considering is 0, minus 1. Here is 0, minus 1, you see, dot f1, f2. And the variable goes from 0 and y. Okay. Now, let us be a bit more explicit, just introducing the coordinate and performing the dot products. So, in the next passage, we have the first term that comes from the first term in the previous one. So, we have the dot product with 1, 0. So the only surviving component is f1. So here we have just f1. And the argument of f1 is given by the parameterization. The x-coordinate is x plus t, and then we have y, and we integrate in dt. Okay? This is what we do for all terms in the expression that we wrote down. So for the second term, we have the integral from 0 and delta y, and the only surviving component of the field is the second, f2, this is f2, and the parameterization this time is on x plus delta x. This is a vertical side, here it is, with x coordinate x plus delta x, and then we have y plus t as a second coordinate, okay? Just that. For the third coordinate, the result of the dot product is minus f1, and here we have minus f1, and here inside just the coordinate. And then for the fourth, the only surviving term is minus f2. Okay, and this is the other passage. Now let's move forward and do another passage. And in the new passage, the two first terms, the first and the second term, are untouched. we focus on the third and the fourth, that I rewrote in blue to stress the fact that we are working on that, and we do something very simple. We introduce a new variable tau. For the first integral, tau is equal to delta x minus t. Okay? So instead of delta x minus t, here we have tau. Then we have to modify the extreme of integration, that result to be exchanged. So we start from delta x and we go to 0. And of course the differential dt is now minus d tau. Sorry, here there is a mistakes. This is d tau. Okay? And the same we do for the last term. We start from here and we define a new variable tau is equal to delta y minus t. So we end up with, sorry, here there is a mistake. This is x plus delta x. This is not an essential mistake, but this is x. Are we sure? Oh, no, sorry, it's x. It's correct because it comes from here. X, not x plus delta x. So I rewrite it as before. And notice that again here we have the differential here, which is dt becomes minus d tau, and there is an exchange between 0 and delta y in the extremes of integration. Okay. Let's move one step forward. And so we do two things. The first thing we do is collect terms referring to the same component of the field, which means in this case the two terms referring to the horizontal sides, the first and the third side of the rectangle. And what we do here, okay, the first term is rewritten as it was before. For what concerns the second, notice that here there is one minus here, another minus here, and then we introduce a third minus that comes from exchanging here and here. So we have three minus signs, then this means that we end up with a minus. Minus, minus, minus equal to minus. Another number of minus is minus. Okay? But now we have the integral going from 0 to delta x, and we have not minus d tau but plus here, and we can change the name from d tau to dt. Nothing changes. And this is the final expression, which is very simple, because we have an integral of the same component. Also the x coordinate is the same. The only thing that is changing is the y coordinate, and there is a minus sign here. Okay? Exactly the same procedure for the next term. In the next term, we gather together the terms with F2, so the second component of the field, and this means that we are referring to what happens on the vertical axis. And then we do the same reasoning as before, so there are three minus signs in the second integral, minus here, and we exchange the extremes of integration. So we end up with a minus sign, integral from 0 and delta y, and here, instead of d tau, we write dt. It is just a change, not a change of variable, but simply a change of name of the variable, change of symbol, so really elementary. Okay? So here we are. And so we are almost at the end. And what we do here, the new thing here is in red. So consider this first term. This first term is a rewriting of this first term. And now notice that here we have a difference of the same function f1 with the same first argument, only the second is changing. So this is the increment of the function f1 when the only variable that is changing is the second one. So this is equal to differentiating f1 with respect to the second variable and then integrating between the extremes y and y plus delta y. We integrate in a new variable that we can call y prime. And we have to put a minus sign, okay? Why minus? Because here, as it is written, it is not the function computing in y plus delta y, upper extreme of integration, minus the function computing in y, but it is exactly the opposite. And this is what we find. Exactly the same procedure we apply to the second term. Okay, so the external integration again in dt does not change at all. And for what concerns the internal integration, we notice that here we have the same function f2 with the same second variable y plus t. So we can obtain this difference by integrating the partial derivative of the function with respect to the varying variable, which is x. And now the integral is in x primes and x prime that runs from x to x plus delta x. Up to here it is all exact, there are no approximations, okay? And at the end what I do is just a change of variable, okay? I want to use not the variable from 0 to delta x or from 0 to delta y, but just a variable from x to x plus delta x and from y to y plus delta y. It is just a matter of choice. If you want some aesthetic, but it helps us to go towards the result. So look at the first integral, how to move this extreme of integration to this one, but simply introducing a new variable x prime, which will be x plus t. So t going from 0 to delta x becomes x prime going from x to x plus delta x. Okay? And the new expression of the integrand is that. The same we do for the second variable. The same we do for the second term, and we introduce y prime, which is y plus t, and this is what we get. And now the last observation is the following, is that here we are integrating on the same region. Okay, the order is different, but you know by Fubini theorem that the order doesn't count. Here we are on rectangles moreover, so in the integral of y, in the internal integral, there is no mention of the external variable, so you can exchange the order as you want. The regularity on the field we suppose is sufficient to do that, so we are completely safe. We can change the order of the integral, or we can write both integrals in a very simple way as a double integral on the two-dimensional domain di, which is nothing but the interior of the rectangle. This is di, which is the interior of the curve ci. Very easy. And so what we have at the end, we can get rid of the prime, And so we have the area integral, the standard two-dimensional integral, and the integrand is this one. Of course, I have to cancel this prime. And this is exactly the content of the Green theorem. Exactly the content of the Green theorem on a rectangle. So Green's theorem on a rectangle is very exact. It is just a sequence of elementary passages. Here there are no approximation, everything is exact. So why isn't it a mathematical proof? Okay, this is the first delicate point, but I think if you followed up to here, we are able to follow also this part. So it is very not very, but it is a bit more delicate than before, because first you have to recognize that this reasoning only applies to this sort of internal rectangles. We used heavily the fact that we are dealing with rectangles because we explicitly parametrized the rectangle here. These are parameterization for the rectangle, and we heavily used this parameterization. But Green's theorem does not hold only on rectangles, it holds on curves like that. Of course, here there are internal rectangles, but what happens when we go to the border, to subdomains that include one side on the border? The answer is very simple. This reasoning does not apply to domains including the boundary of the region of integration. Does not apply to here. Does not apply to here. So let us see whether we can have an intuition of why this does not affect the result. So we prove that Green's theorem holds well here, and so holds well in the part of our grid that does not touch the boundary. For instance, also this holds here, 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 and here, here, here. Okay, also this guy here, this guy here. Okay? If I did things well, so let me change color. If I did things well, this brown contour, is the boundary of the region on which we proved Gauss-Green formula. Of course, this is not the whole region. So what is the problem? How can we get rid of this hindrance? We get rid of that by observing that as the grid becomes finer and finer and the rectangles thinner and thinner, the yellow region becomes larger and tends to invade all the region inside the curve. This is the key observation. This is why it is necessary to raise the number of rectangular to make a partition which is always finer and finer. We can see this fact in a sort of different way, as I wrote it here. So let me write here this observation because I think it is quite nice. The region occupied by internal rectangles on which the theorem holds, on which our proof holds, this becomes larger and larger as the partition becomes thinner and thinner. And now let us write what I wrote 10 minutes ago. The important argument here is that the contribution of the boundary terms, which means the terms like this one, with one side on the boundary where our previous computation does not apply. So the contribution of the boundary terms becomes negligible as the partition is made finer and finer. Another way to see this is the following. Indeed, if you partition the domain with n vertical lines and also n horizontal lines, it is not necessary that it is exactly the same number, but consider the case in which you have n vertical lines and n horizontal lines. As n goes to infinity, which means as the partition becomes finer and finer, the number of terms containing an element of the boundary becomes proportional to n. This is a bit more delicate, but in some sense, the contour, the perimeter of this guy here becomes proportional to the number of lines. Okay? It will be, roughly speaking, 4n, but perhaps more than 4. But it is proportional to that. Because n, so if you want, when making it thinner and thinner, you are changing the unit on which you measure the contour. Okay? So as this unit becomes 1 over n, and the length of the contour is constant, then in the limit you get something which is proportional to n. Whereas the internal terms, referring to true rectangles in the interior region of the curve C, is proportional to the square of n. Okay, the number of rectangle here tends to reach n squared, because you have n horizontal line and n vertical lines. So at the end, when computing the area occupied by rectangles and the area occupied by subdomain containing part of the boundary, you are comparing n squared with n, and n squared is infinitely much larger than n. And this is why one requires the partition to become finer and finer. Okay, so as an homework, then we can discuss a bit. I write it by pen. So apply Gauss-Green theorem to the irrotational but non-conservative field which is the irrotational but non-conservative field, the usual one, F is equal to minus y divided by x squared plus y squared, x divided by x squared plus y squared on the circle of radius 1 centered at the origin. What do you find? Y And in the next lecture, we will try to discuss a bit that. We enter again something which is somewhat subtle. Okay, this is the most subtle part of these topics, and I would say the most subtle part of all the course of mathematical analysis too, but it is very important to understand it very well, not only for mathematical 2 exam, but also for physics 2. It is very conceptual and very deep. So good work, and see this video several times if you need. Don't be ashamed of that, because it is normal. It is a part which is not very standard. It is not just like computing integrals. It is like understanding something which is absolutely non-trivial. Okay? Good work.